All right, welcome. Today, we're putting on our detective hats to investigate one of the biggest mysteries out there, the atom. We all kind of know it's the basic building block of everything, right? But the story of how we figured that out? Well, it's a real detective story, full of twists, clues, and some seriously brilliant investigators. So grab your magnifying glass and let's get into it. So let's start with what seems like a simple question. What's the smallest thing in the universe? For thousands of years, people were pretty sure they had the answer. But as you're about to see, every single time we thought we'd hit rock bottom, a new secret trapdoor opened up, revealing an even smaller and honestly much weirder world inside. Okay, so our investigation starts way back, over 2,000 years ago in ancient Greece. The first clue is in the name itself. The word atomos literally means indivisible or uncuttable. The idea was pretty straightforward. If you take something, anything, and just keep cutting it in half, you'll eventually get to a particle so tiny that you just can't cut it anymore. And that was the atom. Now, for centuries, that was just an idea. Something philosophers debated. But then, in the early 1800s, a scientist named John Dalton came along and created the first official profile of our suspect. He pictured atoms as these tiny, hard, indestructible little spheres. Simple. According to him, all gold atoms were identical to each other and totally different from, say, all oxygen atoms. It was a really neat and tidy theory. But here's where the plot thickens. Dalton's neat and tidy theory, it started to fall apart pretty quick under cross-examination. He said atoms were indivisible, but we now know for a fact they can be split. He said all atoms of an element were identical. Turns out, that's not quite true either. These little contradictions were the first loose threads the detectives started to pull. So how did this solid, supposedly uncuttable atom get cracked wide open? Well, it took a whole series of brilliant scientific detectives who just followed the evidence, even when it led them to places nobody expected. This is where our investigation really starts to heat up. And here they are. Meet our lead investigators and their major breakthroughs. In just a few decades, from the late 1800s to the early 1900s, these four scientists completely flipped our understanding of matter on its head. Each one of these discoveries was like finding a crucial clue that changed the entire direction of the case. Let's start with the first piece of evidence. So the first mystery popped up in the lab. Scientists like William Crookes were zapping electricity through these glass tubes that had almost all the air pumped out. And when they did, they saw these mysterious blue rays streaking through the tube. They called them cathode rays. But what were they? Were they a type of light? Some kind of weird energy fluid? Nobody had a clue. Then J.J. Thomson cracked the case in 1897. He did something clever. He put electrically charged metal plates around the tube. And what he saw was that the mysterious ray bent towards the positive plate. And as we all know, opposites attract. This could only mean one thing. That ray had to be made of tiny, negatively charged particles. And boom, just like that, the case was blown wide open. Thomson had discovered the very first subatomic particle, the electron. It was a tiny, negatively charged piece that was coming out of atoms. This was an absolute bombshell. It was the first real proof that the atom was not indivisible. There were smaller pieces inside. But you know how it goes in these detective stories. Solving one mystery just opens up a new one. If atoms have these negative little electrons in them, then why is most stuff, like the chair you're sitting on, or you, or me, electrically neutral? It just didn't add up. There had to be something positive inside the atom to cancel out the negative charge. The hunt was on. The next huge break came from Lord Rutherford. He set up this brilliant experiment where he fired tiny particles at a super, super thin sheet of gold foil. Now, he expected them all to just zip right through. And most of them did, but every once in a while, one of them would bounce back. It was shocking. Rutherford himself said it was like firing a cannonball at a piece of tissue paper and having it come right back and hit you. He realized the only way this could happen is if all the atom's positive charge, the protons, was packed into an incredibly tiny, dense center, the nucleus. So now our lineup of suspects is getting pretty clear. We've got these negative electrons buzzing around a tiny, dense, positive nucleus full of protons. We're getting really close, but there's still something that doesn't quite add up. There was one final, crucial piece of the puzzle still missing. And here it is, the final puzzle. When scientists looked at an element like helium, they knew it had 2 positive protons in its nucleus and 2 negative electrons orbiting it. Simple enough. But when they actually weighed the atom, its mass was about 4 times heavier than a single proton. The electrons weigh next to nothing, so where was all that extra weight coming from? And the case was finally closed in 1932 by James Chadwick. He discovered a third particle, one that was hiding in the nucleus all along. This particle had no electrical charge. It was neutral, but it had almost the exact same mass as a proton. He called it the neutron, and it was the missing piece that solved the mystery of the atom's hidden weight. And there you have it, the complete profile. Case closed. Inside every atom, we have our subatomic trio. In that dense center, the nucleus, you've got your positive protons and your neutral neutrons. That's where all the weight is. And orbiting way out on the edges are those tiny negative electrons. This is the picture of the atom we still use today. Okay, so now that we've identified all the suspects, let's see what they actually do. It turns out that one of these particles is way more important than the others when it comes to an atom's identity. It's like a unique, unchangeable fingerprint. And that fingerprint is the atomic number. It's super simple. It's just the number of protons in the nucleus. That's it. That one number tells you exactly what element you're looking at. You could say it's the most important number in all of chemistry. Just look at the evidence. An atom with 1 proton is hydrogen, always. An atom with 6 protons is carbon. End of story. The number of protons is the one thing that makes it carbon. You can mess with the number of neutrons or electrons all day long, but the second you change the number of protons, you have a completely different element. Okay, so protons give an atom its identity, its name. But what gives it its personality? What decides how it's going to behave and who it's going to hang out with? For that, we have to look away from the nucleus and out to those electrons. It's all about the electron dance. You know, the driving goal for almost every atom in the universe is just to be stable. And for an atom, stability means having a full outer shell of electrons. Think of it like a dance floor at a party. Everyone's most comfortable when it's perfectly full. So to get to that happy, stable state, atoms will do whatever it takes. They'll give away electrons, they'll steal electrons, or they'll even share electrons with a neighbor. And there are 2 main ways they do this. Look on the left. Sodium has this one lonely electron in its outer shell. It desperately wants to get rid of it. Meanwhile, chlorine over here is just 1 electron short of a full set. So sodium just transfers its extra electron over to chlorine. Bam! They're both stable, they're both happy, and now they stick together. On the right, you've got 2 oxygen atoms that both need more electrons, so they make a deal to share them instead, forming a really strong connection. And what's amazing is that when you map all this out, this beautiful hidden order starts to emerge. This chart shows how the electrons are arranged for the first 20 elements. You see the patterns? Elements in the same column tend to have the same number of electrons in that outer shell, which is exactly why they behave in such similar ways. It's this incredibly elegant system, and it's all built on a few simple rules. So, there you have it. Our detective stories started with this ancient idea of an uncuttable sphere, and it led us down a rabbit hole into this complex world of protons, neutrons, and dancing electrons. And from the simple rules that govern these tiny, tiny particles, the entire universe is built. Every star, every planet, you and me. It really makes you wonder, doesn't it? What else are we missing? What other clues are out there, just waiting to be found?